During the last tutorial video, we have discussed the distance vector approach for the dynamic routing. And today I would like to discuss the link state routing approach, how it differs from the distance vector routing and how it could be implemented. So, different from the distance vector routing, routers running link state routing algorithms exchange states of the link in the network. And link state includes, of course, a metric, cost of the link, and also the information about the vertices that this link connects to each other. Using this information, every router builds its own network graph and later runs the Dijkstra algorithm to determine best path to every destination network. So different from the distance vector approach, in this case every router has a full map of the network, a full network graph, and therefore it could easily avoid routing loops. Let's see how it works using the open shortest path first protocol as an example. So this is, of course, a link state protocol that uses the ratio of reference bandwidth to the link bandwidth as a metric, and the routers exchange with each other a link state database with states of all the links in the network, and it's based on the Dijkstra algorithm. Let's take this network as an example. So as soon as OSPF, Open Shortest Path First protocol, uses network bandwidth, we now display the bandwidth here, and we have 4 routers A, B, C, and D, and also 4 destination networks: network 1, network 2, network 3, and network 4. So let's take the reference bandwidth to the maximum, set it to the maximum bandwidth we have in the network, namely 100 megabit per second, and calculate the metrics for the cost for every link in the network. So, for example, for this link, for every link we need to divide the reference bandwidth of 100 megabit per second to the real bandwidth of the link. For this link it will be 100 divided by 1 is 1. So similar here we divide the reference bandwidth of 100 to 10 megabit and get the metric of 10. And similar for all other links, 2, 5, 2, 5, and here 20. So we have 5 megabit here. 100 divided by 5 is 20. So the smaller cost of the link or the smaller metric always means the higher bandwidth and higher preference for the router. After initialization, each router first of all measures this link bandwidth for all directly connected links. For example, for router A it will be links to the network 1, to the router C, and to the router D. And then after the bandwidth is measured, it selects the reference bandwidth and calculates the metric, and then saves it into the link state database, and then exchange this database with all other routers in the network. Link state database looks like a table where each value represents a link from one node, from one vertex to another. For example, this value means that there is a link from router C to router A with a bandwidth with a metric of 10. The links from the destination networks to the routers are always, the cost in this case should be always set as 0. However, in different order, the links from the routers to the destination networks from the router A to network 1 should be calculated in a usual way. So from the table we can see that the link from the router A to the network 1 has a bandwidth, has a cost of 5. From the router B to network 2 has a cost of 2. From the router C to network 3 has cost of 20, and the similar for the router D. The cost for the link from router D to network 4 is 10. Then the routers exchange this information until every router has the same link state database that looks in this way and is the same for all the routers A, B, C, and D. Only after this step, routers can start, after the link states are exchanged with all the routers in the network, they can start calculation of the best path to any destination. Let's see it on the example. So to find the best passes to each destination, every router, let's take router A for our example, first of all builds from the link state database a graph where where the vertices are routers and destination networks, and the ways of the edges is presented with metrics or costs of every link. Then router A is our starting point, and router A follows the Dijkstra algorithm to find the shortest passes to the all other destinations, all other vertices on this graph. This is how Dijkstra algorithm could be described. So first of all, router A should set distance for the start vertex, which is router A itself, to 0, and set distance for all other vertices as infinity. And then router A goes through all unvisited vertices. Now we don't have any visited vertices on our graph, so it goes through all vertices and selects the vertex with minimal distance. So in our graph now we have a distance for the vertex A equal to 0, and all other distances are equal to infinity. So we should select vertex A. And for every unvisited vertex, we took their neighbors. So for unvisited vertex A, the neighbors are N1, C, and D, and calculate the distance to this to every neighbor. So for the vertex N1, the distance will be the distance of vertex A itself plus the ways of the edge between A and N1. So 0 plus 5 equals 5. And if this resulting distance of 5 is less than the current value for N1, and the current value is infinity, and 5 is definitely less than infinity, so we should update the distance for the vertex N1 and also save the parent vertex. So this 5a means that the vertex N1 could be reached with a distance 5 through the vertex A. Then we go to the next neighbor. Next neighbor of A is C, and the distance will be 10, 0 plus 10, which is less than infinity, so we should update again the distance for vertex C, and do the same for the vertex D. 0 distance of vertex A plus 2 is 2, that is less than infinity, so the vertex D could be reached through the vertex A, and the distance of the path is 2. Now, when all neighbors of vertex A are, when we have iterated through all neighbors of the vertex A, we could mark it as visited and go back to this state. So we again need to select the vertex with minimal distance. All others, these 4 are infinity, and we have vertices with distance 2, 10, and 5, and 2 is the minimal distance. So we select vertex D. And now we, after we selected the vertex D, we check all unvisited vertex neighbors of the D. This is C and N4. So for them we calculate the distance in the similar way. So for N4 it will be distance that vertex D has, 2 plus ways of the link 10, it will be 12. As soon as it's less than infinity, we update and save the D as a parent vertex here, and we do the same for C. So the distance of D plus 5 is 7. 7 is less than 10, so we should update the path, the distance to the vertex C, and also update the parent vertex and set it, change it from A to D. Now when we checked all the neighbors of D, we could mark the D is visited, and again go to this stage and select the vertex with minimal distance, which is now N1. N1 has no neighbors, so we could immediately mark it as visited and go to the next vertex with minimal distance. This is C, and for all unvisited vertex neighbors, so C has 3 neighbors, B and 3 and D, but D is already visited. So we go through B and N3 and calculate in the similar way the distance. So 7 plus 1 is 8, and we update the distance for the vertex B, and 7 plus 20 is 27, which is less than infinity. And we update the distance for the vertex N3. After this step, as soon as all neighbors of C are checked, we mark the C as visited and go next to the vertex B as soon as it has a distance of 8, and check its only unvisited neighbor N2, updating the distance 8 plus 2 equal to 10 through the B. And next we mark it as visited and go to this vertex, which has no unvisited neighbor, and we immediately mark it as visited, and then to vertex N4, and finally to the vertex N3. So now we have calculated the distances to every vertex in this network, and router A can now select the best path to every destination. Let's now imagine that router A need to forward the packet to the network N2. So it checks the N2 node and finds out that it is reachable with a distance 10 through the router B. Then on the router, on the node B, B is reachable with a distance 8 through the vertex C. C is reachable with a distance 7 through the vertex D. And finally D is reachable with a distance 2 through the A, which is our router itself. So the router A can now reach any destination using the optimal and the best path. That's how the link state routing works, applying the Dijkstra algorithm to the full map of the network and finding the best passes to every destination for every router. However, sometimes link state approach is not the most efficient. For example, let's take the internet, which consists of 500,000 networks and have a lot of links between these 500,000 networks. The link state protocols, as soon as they use the Dijkstra algorithm, which is computationally heavy, would take a lot of time and computational resources for routers to calculate such a big network. That's why currently the routing protocol which is used in the Internet core is Border Gateway Protocol, which is a path vector protocol, and it combines the link state and distance vector approaches. So instead of exchanging the distances for the destination network, it exchanges the best passes for the destination networks. And so this exchange still allows this protocol to work as simple as a distance vector approach and don't require such a complicated algorithm to be run on each router. And on the other hand, thanks to the best path information, it could avoid loops and behave better than the distance vector approach.